All right. Good afternoon, everyone. Everyone there? Okay. Just making sure. Yeah, Wednesdays. It's tough day. You're halfway there in the week. Half of you wants to go take vacation because tomorrow is Veterans Day and you don't have work or school or whatnot. The other half is like, oh, I need to keep on working and studying for this MCAT, right? So I'm glad that you guys are here. You haven't taken off on vacation. So let's get started. And today we're first going to talk about thermal chemistry, and then second half of class we'll talk about kinetics. Okay. So thermal chemistry first, talk about the ways that energy is transferred. We'll talk about a heat engine and a heat pump. Talk about a Carnot engine. So let's start with thermal chemistry. First thing we need to talk about is on our energy diagrams. So energy versus your reaction coordinate. So this is a type of graph where your reactants start high and your products end up being low or stable, right? This is typically a favorable type of reaction. We call it spontaneous because the Gibbs free energy of the system is considered negative, right? Realize from here to here, this is your Gibbs free energy, the difference between the products and reactants. And from here to here, this is your activation energy. Okay. This type of reaction is an exergonic reaction. You guys think of exothermic, but that only has to deal with one type of energy, right? The heat energy or the enthalpy of a reaction. But exergonic refers to all energy in a reaction. The other type of reaction you can have is where your reactants start low in energy, overcome a high activation energy barrier, and end up with some lower energy, but higher than your previous starting point, right? This type of reaction is typically unfavorable. This Gibbs free energy is positive, right? This is a typical endergonic reaction. Once again, this is your activation energy. This is your Gibbs free energy that you had to put into the system. So what we're going to see when we compare thermochemistry and the type of energy we have associated with it, looking at kinetics. And you think about it, endergonic and exergonic, they're the same as exothermic and endothermic. Very similar to the terms of shape. Exo means you're giving off heat to the environment. Ender means you're absorbing heat from the environment. Yeah. Exer just means it's giving off energy, right? Heat is exiting the system. So later, when we talk about it, kinetics, which is the second half of what we're going to talk about, is all based on that. No worries. The activation energy. So kinetics is always dependent upon getting to that transition state. So the transition state is this state up here. No problem. It's the transition state up here that we're trying to get to, right? That's what we're going to determine later for kinetics as your rate determining step. Okay. So getting to that transition state means you have to overcome this activation energy barrier. Okay. So kinetics is always determined by, the rate of kinetics is always determined by the activation energy that you have to overcome, right? Versus the thermodynamics, which we're going to simplify and call it thermochemistry, is simply the Gibbs free energy and the equilibrium constant that we have to go over. The Gibbs free energy, delta G, is equal to delta H, which is enthalpy, minus T delta S, right? This is enthalpy. This is entropy. Kinetics is, so someone's asked me to define what kinetics is. Kinetics is the rate of reaction. How fast is reaction happening? Thermodynamics looks at the energy of a reaction and how stable that reaction is going to be. Thermokinetics is just same thing as kinetics. It's all due to the heat that's causing those molecules to want to collide with each other. Temperature is usually in kelvins. Thanks, Monica. Equilibrium constant. Okay. Equilibrium constant. So given a, let me pull it up. It's all right. I'm going to explain what the equilibrium constant is because apparently you're not the only one that has that question. I've gotten emails about it. So let's say we have a reaction. Yes, it's a constant. Let's say we have a reaction A. So let's go over what KEQ is. The equilibrium constant. Ka is just the equilibrium constant for acid dissociation. No, it's the same. Do I need to go over what equilibrium constant is? I know that there was like a lot of like talk about it from students. All right, let's go over it. So given something with gas, something that's solid. Oh, there's other people private messaging me, Monica, saying that they want to go over what equilibrium constant is. Sorry. There's more than one. But yes, thanks for clarifying Michaela's question. The KEQ is just the equilibrium constant in general for anything. Ka is specifically for acid dissociation. Kb is for base hydrolysis. But I'm going to go over what KEQ is, and KSB is for solubility. But KEQ, so this is your forward rate. This is your reverse rate for that equilibrium constant. And let's say we have two molecule C that we're creating that's also a gas. So KEQ keep in mind that KEQ here is simply the concentration of gas C squared all over gas A. Notice that we ignore solids. So let's write the rules for writing KEQ. So stoichiometric values in balanced equation become exponents. This value is this value here, okay? In KEQ expression. 2 does not include solids or liquids in KEQ expression because they exist in excess. So only gases or aqueous solution. 3, KEQ only changes with temperature change. Because when you change the temperature in a system, you change the energetics at which the molecules are colliding. And in doing so, you change the rate at which it's going forward versus the rate that it's going in reverse, okay? So that's your KEQ review, okay?
Hello, will you repeat the third statement? It's not showing on my screen.
Sorry, thank you. The equilibrium constant only changes with temperature change. So when you change the temperature of a system, you're changing the kinetics or the energy associated in which the molecules are going to collide, right? They're moving with more kinetic energy. So it'll collide at a faster rate. K forward, K reverse. KF and KR. Forward rate and reverse rate. And when we talk about kinetics, we'll talk about the rate constants for those. Okay? Thank you. Yes, if you have questions and you can't see something and I don't see you in chat, please speak up. Today we have a lot to go over. Okay? Cool. So the other, this is your first Gibbs free energy equation. We'll go over enthalpy and entropy. The other Gibbs free energy has to deal with your equilibrium constant. That's negative RT, universal gas constant, times temperature, times natural log of the equilibrium constant. We used this equation before when we determined our Nernst equation. So this is our standard Gibbs free energy when we're at equilibrium state. Given the KEQ or given how much Gibbs free energy, enthalpy or entropy that you have changing in our system, okay? So now let's talk about enthalpy, since we're still on energetics. So enthalpy is simply our bond energy, right? So we can define enthalpy as bond energies. And remember when you guys had to do it with enthalpy, you always ended up looking up these numbers in tables, right? So with bond energies, delta H of a reaction, delta H of bonds formed minus delta H of bonds broken, okay? That's generally how you did it when you guys did it in class. The way that they did it through tables at standard temp and pressure, they gave you what we called heat of formation. And so the MCAT can still give you tables of heated formations for certain type of bonds. So heated formation is simply the heat absorbed slash produce when making a compound at standard temp and pressure, okay? There are certain elements that have a zero heat of formation when they're formed. Delta H of formation is equal to 0 if the element is already in its most stable form. So certain molecules, diatomic gases, and liquids that you need to know that have zero heat of formation. So if they show up and you have to deal with bond energies or enthalpy, you know that they bring zero heat of formation to the table. So you have your nitrogen, you have your hydrogen, fluorine, oxygen, iodide, chloride, bromide. So these diatomics, nitrogen, hydrogen, fluoride, oxygen, iodide, chloride, and bromide have zero heat of formation. The way I remember this, this is my mnemonic to remember it. Never have fear of ice cold beer. N is never, have is hydrogen, of, I guess, is oxygen, or as oxygen and fluorine. Ice is your iodine, cold is your chlorine, and beer is your bromine. Okay, so that's my mnemonic to help remember this. So this is, these molecules always end up having no delta H of formation. So there's no bond energies between, right? Because literally you're taking bonds broken minus, or bonds formed minus bonds broken, okay? Within your system. The third way that you calculated for enthalpy is using calorimetry. And what calorimetry does is it measures delta H, right? So this is that experiment where you had like styrofoam environment, and then you had a thermometer that was stuck in. There's liquid in solution. There's a magnetic bar that rotates and spins. At the bottom, we called it the ebulator, right? And what ended up happening, yeah, you can call it bomb calorimetry, but still just calorimetry. Bomb calorimetry is like having to deal with explosions and stuff, right? This is just taking a look at the heat given off to water, heat gained in water, right? It's a little bit more gentle, but yes. So what you end up getting is that delta H of your system, whether it's exothermic or endothermic, is equal to the negative of your heat that you have in your system. It's an ebulator. Didn't you remember putting that bar magnet on the bottom and having it spin around so the liquid would rotate? Yes. Yeah. So that's what the thing is. Yeah, it's like a little pill. It looks like a little pill, but it's just a piece of plastic with a metal piece inside. Yeah, it's a magnetic stir bar. That's literally what it is. Right? Ebulator is just a fancy name of like making waves. Yeah, same as what you use in distillations, right? Because the whole point is to get it to be uniform in nature for the temperature to distribute evenly, right? In the experiment, and for the liquid molecules to be moving so that they have greater collisions too. So heat energy, we've already gone over, is mCp delta T. We worked over this in work and energy. And you measured this, right? And the enthalpy was negative of that heat. So if the temperature went up, right, that meant that the experiment was exothermic, right? Because energy had to leave the experiment in order to heat the water up. Or if the temperature went down, that meant that the experiment was endothermic because it took heat energy from water to do the experiment. Okay, so that's why delta H is equal to negative Q. Cp is heat capacity at constant pressure. P. C subscript P. Pressure. Heat capacity at constant pressure. Okay. And go back and look at work and energy. This is an equation that I've already covered before. The difference is here, when we're looking at this heat energy, we're looking at what's happening in water, right? Which means if water temperature goes up, that means the reaction was exothermic or exergonic, right? And if water temperature goes down, then that means the reaction was endergonic and it sucked up energy from the water. Do you need me to rewrite heat capacity at constant pressure? Okay. Thank you. All right. These are the three ways that we would measure enthalpy, right? You did it through tables by taking bonds formed minus bonds broken, right? Using the heater formations for when you were at standard temperature and pressure. The other way is when you did it using bomb calorimetry, right? Or just calorimetry in general. So with heat energy, heat can be transferred. So let's look at the ways that heat is transferred. Okay, first way is convection. This is currents. Heat is transferred from currents in the fluid medium. either through gas or liquid. And you think about it, what do we have that we use every day that uses convection? Right? It's in the name for the device. Your oven. Perfect. Yay. Yes, microwaves use convection too. But realistically, microwaves use convection because of the fan in the back and its radiation from microwaves that actually heat things up. As a convection oven, it uses heating elements and it blows that heating element across the top and the bottom of whatever you're trying to cook, right? You also use it when you use and decide to cook sous vide, right? If you ever cook something sous vide and in like Ziploc or, vacuum sealed bags or in a liquid environment, you're still cooking by convection, right? So it's heat transfer from whatever the heating element is, whether it was your microwave or your heating coils in your oven, through the gas or liquid medium. Okay, so that's convection. So when you think about like cooling yourself off and blowing, you're transferring heat using a fluid media. That's convection. Okay, this is how heat is transferred. The second type of heat transfer is conduction. Hopefully everyone's eaten, because every time I think of all these heat transfers, I think of cooking. Conduction is heating with a gradient, like from hot to cold, through a solid medium. So this is like when you barbecue, right? You're putting the meat onto the grill, or when you're cooking in a pan and you're putting your protein or vegetables onto your pan, right? The heat is being transferred from the solid medium of the metal onto whatever you're cooking it on, okay? Or whatever you're trying to cook on that surface. So it goes from a cold or a hot environment to a cold environment, right? And it makes sense. If you think about it, where is it heating up? So depending on where your fire is in your grill, that's where the heating element is going to be hottest. As you get further away from it, it's going to be colder, right? So they always tell you if you're barbecuing, you need to have different heat areas to cook things, because certain things need to be cooked slow. You need to put a nice sear on it so that it seals in the liquid or fluid, and then you move it like at furthering heat gradient so that the inside can cook at a slower pace. Otherwise, if you cook everything on high, you're going to burn everything. Okay. So conduction is heating with a gradient. So going from a hot to cold gradient across this solid medium. So convection is liquid and gases, and conduction is through a solid medium. Gas. In the fluid medium in the oven is gas. Right? The fan is blowing the hot air above and below your roast, your turkey, whatever. It's just atmospheric gas. It's not like some special gas. But yes, that's what you're cooking with, right? You're heating the air up with your heating coils on the top and on the bottom, and the fan in the back blows it so that it circulates above and below your bird, your roast, whatever you're cooking. Lasagna last night. Oh, it was so good. Yeah. So convection oven, super useful for nice, slow cooking, right? Getting those nice gradients across your meat. Last but not least, the last form of heat transfer is radiation. So radiation is absorption and emission of electromagnetic magnetic photons. So every time we heat something, we're giving off some type of radiation, right? So when we burn gas, natural gas inside our house, or when we heat a heating coil up electrically, all those types of heat is coming and it's radiating outwards, or burning coal, right? Or charcoal, and using the combustion from that carbon to give off electromagnetic photons of radiation, right? They just happen to be in the infrared range, or in your system. That's why we see it as typically some kind of yellow, orange type color that we're giving off. And we ourselves are radiating heat, right? Every time we do a biochemical process, every type of reaction that we have in our body is to maintain that temperature that we have constant in our body, whether 98.6 that we're trying to give off. So to keep every process in our body regulated and operating optimally at that temperature. So radiation is the absorption and emission of electromagnetic photons, right? And so things that radiate, like burning of charcoal, heating coils, gas, burning of gas, right? Induction is actually not a form of actual heat transfer. You're right, it is a form of conduction, but we're conducting by, instead of directly sending current into the electric coils or the metal coils to heat them up, right? We send current into a coil that's underneath, and then the material on top is paramagnetic, and then that material gets in turn induces a current inside of that material, and that's why it heats up. So cooking by an induction has no direct electrical energy transfer, but it's through induction, or the movement of current causing magnetic fields, and those magnetic fields cause current inside of your cooking pan. So induction heating is a form of conduction in the end, because the pan itself is getting heated up, but it's getting heated up through an electromagnetic process of magnetic fields inducing current, external magnetic fields inducing current inside of a paramagnetic element, right? When you cook with induction, you have to have a certain type of pan or pot or metal to do it. You can't just take any like cast iron and throw it on and cook with induction. Okay. Yes, everyone loves food. If you master heat transfer, your food will taste amazing. So if you think about it, this is all the stuff we use to cook. Heat transfer is in the toaster, right? But then we're doing conduction, because you're doing direct solid pieces of metal that are heating up, and it's touching your food, right? So that's a conductive element. Yeah. Yes, conduction is what gives you those nice grill marks, the nice Maillard effect. That's conduction, right? Convection is what gives you that moist meat, that juicy rib, right? Because it basically slow cooks it so that the juices get to stay inside, the fats get to melt, they get to emulsify together with your salts, your herbs. Yeah, it's delicious, right? And radiation is what's giving off that heat in the first place, right? Either from heating coils or from gases that we're burning or charcoal that we're burning. So yes, sorry if I'm making you guys hungry, but like that's the best way to remember heat transfer. No joke. Like every time I cook, I think of heat transfer. I think it has to deal with like vection needs to deal with like vectors and currents, right? And conduction is like solid things, right? Yeah, that's why. Only if you render the fat correctly, Sophie. Only if you render the fat correctly. Ducks are good. Typically, ducks are not so great. Funny. Okay. You can't have duck. You can't have foie gras. You can't have pate. Those are so good. Sorry for you vegan people out there. But yeah, I'm like, all those things taste amazing. Foie gras, pate, like you need to have it once in your life. Just try it. It might convert you. And again, it might not. Okay, so now let's take a look at the first law of thermodynamics. So, first law of thermodynamics states that the internal energy of any system is simply the heat plus the work that is done in the system. So we can convert work into force times displacement, and we can also convert work, when we did it with Bernoulli's and with fluids, into pressure and the change in volume, right? So H, no, that's a U. This is internal energy of any gas, capital U. Not an H. Sorry, I know my writing's bad, but Q is heat energy. Internal energy of gas. U is just the total energy of the surrounding environment or the surrounding gases in the system. They'll tell you because you're going to deal with engines or heat pumps, okay? So this is the first law of thermodynamics. Delta U is equal to Q plus W, but typically it's written as delta U is equal to Q minus P delta V, okay? Before we get any further, let's go over some thermal processes. There are four types of thermal processes that we need to know. Isobaric. This is commonly referred to as constant pressure. Isothermal. This is constantly referred to as constant temperature. Isochoric, constantly referred to as constant volume. And adiabatic, this is no heat loss or no thermal loss. So Q is equal to 0. Yes, constant V is constant volume. So constant pressure, constant temperature, constant volume, and heat is transfer is 0 for adiabatic. All of these these first three, isobaric, isochoric, and isothermal, are all ideal conditions. Adiabatic is a real, right? You use this in real life. So the only way to not transfer any heat is to do it super fast, right? So whether you're compressing or expanding something, it happens super fast. And that happens adiabatically, okay? So let's look at the two types of an engine and a pump. So heat engine and a heat pump. We'll do the heat pump first, aka your refrigerator, and then we'll move and talk about your heat engine. Okay. So, first type of machine that you guys need to know is your heat pump. This is typically under thermodynamics. This should have been taught under thermodynamics. Heat pump, heat engines. Sorry, someone was asking, when would have this been taught in G-Chem or general chemistry? When you guys covered thermodynamics, this is heating up, right? And this is the practical application from all that heating up that you guys talked about. So we'll start with the compressor. So heat pump is AKA a refrigerator. Right. And what a heat pump does is you put work in and you get heat out. Right. So the work that's being put in, you hear it every time. You probably don't hear it typically during the day because you're not listening to it. But if you're up at night or you wake up in the middle of the night, and I think most doctors are somewhat closet insomniacs to begin with anyway, you hear it, right? It's that in your refrigerator. That's called the compressor. What it's doing is it's doing work in to turn that gas inside your refrigerator into a liquid. So this is typically an exothermic process that we're doing it. So it's now the liquid inside the refrigerator is heating up. That liquid freon inside your refrigerator. So then we have a hot liquid. In the back. You're putting energy in to the system, so you're using it to compress the gas. It's giving off heat. That's why the liquid heats up. You're taking hot gas and compressing it to make even hotter liquid. Okay. And so this is your back of your fridge. And if you ever installed or put in your fridge, sometimes you guys just move into apartments and the fridge is already there. But I remember, at least when I was in the dorms, I had to get a fridge because the dorms don't supply you with a refrigerator because it's just basically a bed and a desk. And they expect you to eat everything from the commissary, right? Or from the food court. So what ends up happening is I put in the fridge and they tell you in the morning in the fridge, don't put it too close, leave an inch of space, or at least an inch to the 4 inches of space from the wall to where the fridge is. The reason being is that hot liquid is going to give off hot gas, give off that heat. This is your heat out to the surrounding environment. So if it's too close to the back of the wall or it's touching the wall, it could possibly heat the wall, over time drying your wood, over time causing that wood to get on fire. So don't push, in an effort to save room, don't push your refrigerator all the way to the back. Make sure it's about an inch to 3 inches out from the wall. Okay. This is the back of the fridge, and this is where heat is coming out. And if you look at the back of the fridge, you'll see coils going left to right in a zigzag, cross switch pattern. And that's the more surface area it has, the more that heat can be given off. Hey, it helps, not burning down your apartment when you're broke as a student. Super, super useful. Not burning your car when you're trying to hook up your battery and trying to jumpstart your car. Because, when you first buy a car, it's not brand spanking new. So here we're compressing. It's compression. Over here we have expansion. So we're taking that hot liquid and allowing it to expand to a gas. And then this goes into the refrigerator. So this is a cool gas. So this is a cool Freon gas now. And what it does, it absorbs the heat from inside the fridge. Now, these are just coils that are existent in the back of your refrigerator on the inside and on the outside. This is what this little like tube that I'm drawing is. You don't get to see this because there's like a little plastic sheet that usually protects it. And so you don't get to see all of these wires and coils and heating elements. Okay. So you're absorbing the heat from the inside, taking it, compressing that hot gas. It warms up that gas. And then you compress it to make it hot liquid. That hot liquid then dissipates the heat as it flows through the coils from the top going down to the back. Okay. So just keep that in mind. So over here we have expansion. This is the heat out that we talked about. And this is the work in that we put in our heat engine or refrigerator example. Okay. By the way, Freon, which is still used, we're trying to use less of it. It's partially polar, C, Cl, Cl, a methyl group, and a hydrogen. Okay. This typically has a high boiling point because it's polar. Okay. The other case, and then we're going to lead us into the Carnot engine, is your heat engine. And with the heat engine, this is your typical steam engine. And as advanced as most things are, nuclear power plants operate the same way, except the heating element that we use just changes, right? All we're doing is we're putting heat in and we're getting work out of our system. This is dealing with energy and energy conservation. This is one of those application type things that can come up. In terms of high yield or not, it's just come up before in the MCAT, so I'm just going to make sure that we go over it so that you guys understand what's going on. Yeah, someone was asking if this was like a super high yield on the MCAT. This is application of conservation of energy to your thermochemistry, to your thermodynamics, right? And if you think about it, thermodynamics is conservation of energy, and thermochemistry is the amount of conservation of energy from the bonds broken minus bonds formed, right? And Gibbs free energy is the energy that you get released from a reaction from those bonds breaking and the difference between those two, right? Bonds breaking and bonds forming. So this could be the Fulton steam engine. In your system, we're taking a liquid and we're converting into a gas. This is step one, right? You could do it with a boiler, but you can think of it like they could have burned charcoal, they could have burned wood. They use nuclear rods now to get that liquid to turn into a gas. Okay. That goes into a system. It has a valve and it goes into a piston. within your system. Okay, let's describe what's happening. So at 1, we know that we have a liquid becoming a gas. It's heating up slowly. At 2, this is right here. When the pressure is now built up enough because you've been heating the molecules, increasing, the heat or increasing the pressure in your system, right? From your ideal gas law, you can totally see. That pressure then blows, gas enters into cylinder. There's a plate here that is then used to turn a crankshaft or a wheel. That could turn your turbines for your production of electricity. That can turn a axle or rod for rotating your car, your paddle wheel, right? In the original Fulton steam engine, that's what it did. But all of the things are still the same. It turns an engine, right? So that gas rushes in, pushes up on that engine. Then at 3, as that piston begins to fall, so it rises up really quickly, then it begins to fall down really slowly. And as it begins to fall down, gas then leaves at 3 as piston descends. And at 4, that gas becomes a liquid, and then you pump the liquid back and you have it starting all over again. The same thing is, no joke, happened in the steam engine, still happens today in nuclear power plants, and most power plants, whether it's steam operated or nuclear operated or coal operated, they're all the same thing, right? Those are just all different things that cause you to heat up that liquid into a gas, right? Whether it's coal, wood, charcoal, nuclear, those are all heating elements. And from 4, we go from a gas to a liquid, and it cools down. Okay, so this is your typical heat engine or heat pump. And the work that we get out, right? So this is the heat in right here, right? This is at the boiler. You're usually burning something. And the work that we get out is over here. At the rotation of that piston or that crankshaft. Sorry. It goes back down because of change in pressure, not temperature, correct? Yeah, it's actually the weight of the piston. It just falls back down, right? That thing has mass. It's generally pretty dense, and it's going to push its weight back down, so that compresses the gas. It was the high pressure buildup before the valve that caused all that gas to rush in. Once the gas rushed in, it pushed the piston up, that turned the wheel, and then it falls back down, right? And this whole process repeats again. This is Q in and you get work out. The last slide, you did work in and you got Q out. Correct. One is doing work, the other one is just taking heat out. Heat pumps and heat engines are different. Heat pumps are your refrigerators, your AC units, right? Inside your house. It pumps heat from the inside to the outside. And heat engines are devices that get things to move, right? That rotation and that turn of the crankshaft is turning an axle, turning a wheel, turning a paddle wheel, turning a turbine, right, for your power plants. If you guys ever go to Vegas, which I'm sure you guys have at some point, take 30 minutes out of your life, go to the Hoover Dam, watch a turbine, and see how it works. What it does is it takes two magnets, it rotates it using induction. Hey, lap. It gets electrical current to flow. Hey, we're using our knowledge that we learn, right? Yes. So for the fridge working, it allows for the extraction of heat from the food environment inside, right? So if we go back to the heat pump, this is the inside. This is the outside, right, of the refrigerator. So it's sucking heat from the inside and pumping it back out to the outside or the back of the refrigerator. Yes, so hydroelectric dams use what? Potential energy of water. As that water falls, it turns the turbines. So we don't have to use a nuclear plant, but the turning of the turbines, they can have it at any plant, right? It's just two pieces of magnet rotating over each other, creating induction, creating electric current from those moving charges that we had in our systems. What we just talked about on Monday with electromagnetism. Okay, so now let's take a look at a Carnot cycle. And a Carnot cycle is just basically a perfect heat engine and going around one cycle and drawing it as a relationship of pressure and volume. So a Carnot engine, it looks like Carnot. Carnot engine states that all processes are reversible. So, what does that mean in real life? It's run real slow. Okay. So, in terms of pressure and volume, and you've seen this little heat cycle on your MCAT. I'm pretty sure they gave it to you on the AMC practice question or the free AMC test. This type of question comes up quite often. So you start at some starting point A, it goes to B. So here we're taking our Q hot and putting it into our system. And we're getting what? A to B. We have an isothermal expansion. So we're heating that liquid and turning it into gas, but we're doing it really slowly at the same hot temperature. Then at step 2 for my heat engine, it went from B to C, right? What happens as we go from B to C? We have an adiabatic, something that is done relatively quick. That means no heat loss, expansion. That's when the piston goes up and the gas rushes into that cylinder. So temperature goes from hot to cold. Now we have all this room for the gas to expand. They're no longer colliding. They're not giving off heat, right? As the piston begins to fall, right, for going from C to D, we have an isothermal compression. That's what the piston is doing as it begins to fall down at the cold temperature. And last but not least, we have a very fast compression to get back to where we started. So from D to A, we have another adiabatic compression. Going from something cold to something hot, and we're heating it up again. And this is the cycle that we have for our heat engine. Okay. So remember that whenever we have a heat engine, what are we doing? We're putting in Q hot or heat in to your engine. We get work useful out of it and some heat coming out of our tailpipe, right? Heat is given off out of the engine, given off out of the tailpipe of our system. Think of your vehicle or your car or any building. It always has some type of exhaust. That's what QC is. So the equations associated with this is work done by the engine is equal to Q hot minus Q cold. And to get thermal efficiency, it's simply the work that we get out of it, work done by the engine, divided by the amount of energy that we put in the heat hot. So we know that it's Q hot minus Q cold all over Q hot. H. H stands for hot, C stands for cold. That's the heat in and heat out, roughly. Okay? It's not really cold, it's just colder than what we put in. So we can say that, yes, it's useful work. Yes, Carnot engines are an example of an ideal heat engine where no energy is lost in every step of the way. Any engine can be a car engine, right? But not any engine can be a Carnot engine. So car engines, as we know, is not 100% efficient, right? We know that we lose basically 67 or something percent. But this is not losing anything. So 1 minus QC all over QH is your thermal efficiency. We'll call this E. Okay. So all this means is that if for a Carnot engine, QC is equal to 0. QH divided by QH is 1 minus QC over QH. Okay, so for a Carnot engine, we don't lose any heat in the system. So this goes away. There's no exhaust. All that heat that we put in is done usefully. We know that that doesn't exist in real life, but this is the dream, right? If we can actually get an engine to work this way, we would be burning way less fossil fuels to heat up our houses, to drive or fly anywhere, right? To deliver all our goods. But sadly, in real life, we are going to have some heat given off. TH is hot temp, correct? So at the top, when you first start, you're putting heat in, so the temperature is staying hot the whole time. It's just done really slowly, so the temperature doesn't increase. But you're increasing the number of gas molecules in the environment. More gas molecules, more pressure, right? More collisions. This is directly proportional to that heat engine diagram that I drew earlier. Cool. So this is an example of your Carnot engine and your heat engine. So the Carnot engine is a perfect heat engine. The heat engine in general is 1 minus the exhaust heat given off over the total heat that we put into our system, or heat energy that we put into our system. Okay. All right. Now let's switch gears and talk about kinetics real quick. Okay. So remember how at the beginning I talked about activation energy versus the Gibbs free energy. So now let's talk about that activation energy and how it gives you your reaction rates. Okay, and the rate of reaction. So that forward reaction and then a reverse reaction that we're talking about, we're going to go over it. Okay. So kinetics. Kinetics talks about the rate of a reaction. Thermodynamics and thermochemistry talks about the energetics of a reaction. Okay. Kinetics talks about how fast the reaction's occurring, and that is always determined by the rate determining step. Okay. And we talked about that rate determining step. So let's talk about rate determining step. So is the slowest that is exactly right. Someone stated that the difference between thermal and dynamic product and kinetic product is the product that we have at the lower activation energy that happens more quickly. Thermodynamic product is the one that happens more slowly because it has a higher activation energy, and that therefore making that product more stable, which is why we have to wait around in chem lab for so long. Now, if you didn't wait in organic chemistry lab for so long, right, you get a lot of the kinetic product and not a lot of the thermodynamic product. Good point. But yes, that's what happens in a typical reaction. So that's the difference between kinetic versus thermodynamic, right? Thank you for pointing that out. So the rate determining step is the slowest, most different step in a reaction, right? It's typically the transition state of that reaction. It limits the rate and determines activation energy. So, how do we determine this rate determining step for kinetics? This symbol, that's just transition state. Looks like 2 T's. Thanks. Yeah, it's like a notation. I think most TAs use it for transition state, even when you guys were doing organic chemistry, right? You guys just called it what? The tertiary carbocation. The for SN2, it was like that structure where you have the leaving group and the nucleophile attacking at the same time, right? You call those the transition states. Yes, it does say rate, limits the rate and determines the activation energy. Apologies, trying to get through a lot. I'm literally going over 2 lectures in like 2 hours. So the first thing is we have to figure out how do we determine this rate determining step. And the main way to do it is by using spectrophotometry. A. Spectrometer. Okay. And the way we do it is by using Beer's-Lambert law, where it simply states that absorbance is equal to the extinction coefficient times the length of your cuvette times the concentration of your sample. This is your length of test tube or container. This is your extinction coefficient. They will have to give these to you. You're not required to remember them, and this is your concentration. Right? You guys have done this before. Extinction, not extraction. When does that element go away? So each element, depending on how much you dilute it, will stop absorbing light. Okay. So this is Beer's-Lambert law. This is how you would go about doing it. Okay. So you end up getting a bunch of absorbance as a function of your wavelength, right? And at time equals to 1, you have a bump that looks like this, 2 bumps. At times equal to 2, this has now gone down. There's a new object that's here. This has gone down as well. And there's a new object here, right? Time equals to 3. This has continually gone down. This has gone up larger. This has now come back somewhere in between, right? And now this has gone down. Times equal to 4. This gets down even lower. This gets larger even more. This is coming back almost to what it was before. And this is getting less. So if we label these humps as hump 1, hump 2, hump 3, and hump 4, which one, what do you think it is in a chemical reaction? So if the chemical is reacting and we've been taking different absorbances at different periods of time, what do you expect 1 to be? Molecule 1. It's been decreasing the whole time as a chemical reaction happens. Good. The reactant, right? Because eventually it's going to run out and it's been getting less. What about molecule 2? It's getting larger the whole time. Starts off with nothing, becomes more and more and more. What do you expect that to be? Product. Molecule 3, what's happening here? It starts off high, goes low, and then comes back up. Yeah, it's something that reproduces itself like a catalyst. Gets used up during the beginning of reaction, goes down, and after it's done being reused, it comes back And state 4, this is our intermediate. The formation of this is the RDS, the rate determining step. Right? Because it starts, it forms, and then it lowers down because as the reaction goes to completion and you make more and more products, there's less molecules at that intermediate step, that rate determining step. So you would use Beers-Lambert's law, take a bunch of successive pictures of these things, overlay them on each other so you can see what's actually happening over time to each of these molecules that are being created and all these intermediates that are being created and then reused or converted into product, right? In a reaction. Does that make sense? Yes, no, maybe so. Good. Making sure. Okay. So let's look at the ways we can affect the reaction rate. The first way that we can affect reaction rate is with temperature. Temperature, what you see through the Arrhenius equation for the rate constant, some concentration times e to the negative of your activation energy divided by RT, R being the universal gas constant. So what we see is that rate constant K, either the forward or reverse, is directly proportional to temperature. The higher the temperature, the faster your rate constant is going to go. You typically see this Boltzmann distribution, where you have the number of molecules when you talk about temperature. And then the x-axis is kinetic energy added, i.e. what is the temperature that you've added to the system. So there's a lot of molecules at a lower temperature. This is T1. And if you get a higher temperature, there's less molecules, but more of it is at a higher temperature. This is at T2, and we know that T2 is greater than T1. And you'll see this Boltzmann distribution. This is called a Boltzmann distribution. To show you the number of molecules that you have when you heat up a system and how much energy is associated with it. So that's why when we increase temperature, we change the equilibrium constant, right? Because net effectively, what are we doing? We're changing the kinetics of the reaction. So we're changing that rate constant K because the molecules are now, more molecules are moving at a greater kinetic energy, right? So faster velocity, faster chance of collision. And it shifts and changes that equilibrium constant. The other ways to affect the reaction rate is to increase reactants. Oh, I should have totally made the connection. This is like dating, right? Affecting reaction rate, right? Having more reactions, having more relationships, same thing, right? When you increase temperature, you're moving faster, right? Moving faster, you interact with more molecules or interact with more people, right? So increasing temperature means that you have more greater interaction, right? Increasing reactance is like, okay, now you have more guys or more girls, right? To deal with. Like for ladies, going to San Jose, there's like, 5 or 6 guys for every one girl, or feels like 10 for every one girl. But yeah, sorry, I'm from San Jose. We call it Man Jose for a reason. Silicon Valley is mostly a bunch of tech dudes. If you're ever an engineer, you know what I'm talking about. So what do? You go where you can increase the reactance. I went to New York, where there's more women than there are men. So it was great. So that means increased reactance, then there's more available for collision. Right? So what does that mean? That just means that there's more reactants to react with or to collide with to form a reaction, right? The other thing we could do, we could add more solvent. More solvent dilutes the reaction. And slows it down. The reason being, it destabilizes the transition state. So the chances of you finding that molecule to find the perfect transition state, right, is lessened, right? Because there's all this other noise, other molecules that are inert that you will never be interested in, right? So kind of like the real world. When you go out in the real world, there's a lot of noise in your system. Okay, and then the last thing that we could do to affect reaction rate is to supply a catalyst. Sure. So temperature is one way. That means we're increasing the kinetic energy. In real life, you're moving faster, you're more likely to see more people, right? Number 2, increase reactance. There's more available for collision, right? Go to a place where there's more girls. Go to a place where there's more guys, especially if you're trying to find a significant other, right? It's generally not clubs or bars. By the way, guys, yoga, a lot of women. Solvent. If you want to dilute the system, right? Makes it even harder for you to meet somebody. Add more solvent, right? What does it do? It destabilizes the transition state. Less likely for you to meet your true love. Let's leave it at that, right? Your significant other that you are, it's like your soulmate, right? That's what these reactants are doing, right? They're trying to find the right reactant to form the right molecule so that they can become stable, right? Same thing, right? With you guys, when you guys are dating. I did not meet my wife through yoga. The best people that are judges for you are your friends. I met my wife through my middle school friend. I kept in touch with all these years, and we went back and hung out, and turns out that she was friends with him, and apparently we have like a bunch of mutual friends. We went to the same college. We didn't even know each other back then, and then we totally hit it off. But yes, not at yoga. Though we did do yoga on a date, but neither here nor there. But I was like noticing, yeah, there are hardly any dudes at yoga. And if they are, they're gay. And so you can get hit on the other way too. Hey, she took me to the yoga. She wanted to go to do yoga on a date. We're still dating. We weren't married yet. I was like, yeah. I was just noticing. I was like, holy Jesus, there's just a lot of women here. There's like hardly any guys. But I really like yoga. It's like very centering. It's very nice. Gets you to calm down from the hectic world that's out there, right? So many things pulling you into many different directions, right? Okay, so now, Alap, we're good with this slide. I can move back to the other slide. Awesome. So, catalyst. This is for those who are like, I'm too lazy to go out there. I wasn't, I don't want to move very fast. I don't really want to go move to a different city. Well, you know what happens when you don't do things and like find someone and then you get closer to 30, your parents decide to step in. A catalyst is your matchmaker, right? What does it do for you? Let's see. It lowers that activation energy. You don't have to do any work to find your significant other, right? Lowering activation energy. Do less work. It stresses a lower transition state. Someone already did all the work for you, the matchmaker, right? It works because it increases the reaction rate. Lots of cultures use arranged marriages and it still works. And at the end, the matchmaker is free to make more matches. It is not consumed in the reaction. So these are all the things that the catalyst does, right? In your system. Lower energy state, you don't have to go out there, put yourself out there to find somebody. Someone else is going to do it for you. Your parents. And I said, hells no. Then I decided to become more active, doing other things, finding my own interests. But yes, these are all the ways to affect a reaction rate. So now let's take a look at the reaction rate and what's happening in a reaction. So with reaction rates, let's say we have A plus A, little b, B becoming little x, capital X, right? So we define the rate of a reaction is simply K from the Arrhenius equation, concentration of one reactant raised to some exponent times concentration of another reactant raised to some exponent. Both these exponents are determined by experimentation, i.e. they'll give you a table, and as you change the reactants in your system, how does that affect the reaction rate? Okay, they'll give you a data table with that. So, depending on how many reactants are needed, they're broken up into these types of systems. So you can have a 0th order, first order and second order kinetics. So a 0th order reaction, the change in reactants over the change in time is equal to the rate constant times none of the reactants. So if we do our calculus, I'm going to skip all the steps of the calculus and I'm going to linearize it for you. That's a negative sign because reactants are always decreasing. Right? You're going to decrease the reactants, the change in reactants is going to, or per unit time. So this is the reaction concentration at any given period of time minus from the original reactants is equal to that rate constant times K, times T, right? This is your Y, this is your MX, and this is your B, respectively, right? In your system. Your half-life for your 0th order reaction is equal to the concentration, the initial concentration of your reactants divided by 2K. The first order, that negative change of R over delta T, is now going to depend on one of the reactants in your system. And that changes the math slightly. So you get a natural log of your concentration of your reactant at any given period of time over your initial concentration of reactant is equal to negative KT. We can rewrite this as ln of concentration of R sub T is equal to ln of concentration of R naught minus KT. This is Y is equal to B minus MX. Is the ln applied to both numerator and denominator? Correct, it is. There, I'll write it like that. And it's just the difference. Correct, not as initial. When I write sub-zero is at time sub-zero, and at T is any time further down the line. Okay. The half-life, this is Y, not B. The half-life for a first order type of reaction is simply ln of 2 divided by K. It's a constant, not depending on any concentration. The second order, this is going to require you to have both or two reactants in your system. You end up with 1 over the concentration R sub T minus 1 over the concentration of R naught is equal to KT. This is your Y, this is your B, this is your MX. I'm just breaking it down into the linearization, right? You guys do this when you guys did your Lineweaver-Burke from your Michaelis-Menten reactions. You linearize 0 order, first order, second order, right? And then anything with a 1 that you guys discussed in organic chemistry, SN1, E1, that's first order, right? It only requires you to get to that tertiary carbocation for that transition state. And that's what's determining it. Bimolecular or second order requires you have 2 molecules, right? That's your SN2, E2. type reactions within organic chemistry. And last but not least, the half-life for a second order is 1 over K times the initial concentration. So these are all the half-lives for the 0 order, first order, and second order within your system. So within our GChem book on page 236, 237, does a good job of showing your different half-lives and how long it takes to get to each of the half-lives for those systems. So this is on page 236 to 237, GChem book 2. Okay. So if we look at it, half-life looks like the time interval gets halved every time for 0 order for half-life. For first order, time interval is always constant. It's always t. And for second order, time interval always doubles. Okay? For every half-life. So it goes t, then 2t, then 4t for every half-life thereafter. And I love this graph on that page, those 2 pages, because it breaks it down. Sure, for 0 order, half-life is halved every subsequent half-life. So the first half-life would be t, the second half-life would be t over 2, third half-life would be t over 4, so on and so forth. That's for 0 order. First order, which is majority of the questions you're going to get on your MCAT with regards to this information, it's always going to be the same half-life because half-life is constant, ln of 2 over k. Okay. And for second order, the half-life always doubles. So first half-life would be t, second half-life would be 2t, third half-life would be 4t, right? It'll take 4 times as long to get to the third half-life from the first half-life. Okay. Based on their curves that you have of decay for your initial reactants as it goes down. That's basically any problem that you have. We can look at some problems for first order decay in a little bit, okay? And then we'll do a passage too, okay? It just depends on what the half-life is. Like, look, carbon's half-life is 720 somewhat years or 40 years, right? Depending on what book you read. And so every subsequent half-life is always, so first half-life would be 5,720 years. Second half-life would be 5,720 years. Third half-life would be the same amount of time. Does that make sense? So that's how we were able to do carbon dating. And then from that carbon dating, based on the percentage of like remaining substance you have, you can figure out how much you started with and how long it's been decaying, right? So they usually take like a bone, right? And they assume that the bone should be a certain shape, right? And then so that should be giving you a certain relative mass on the system. And then they look at the current mass and they see how much it's decayed over that time. And then they estimate that actual like carbon date. Realistically, it's even more intricate than that. They actually look at the nitrogen that's actually decayed down to carbon 14. Okay, we'll get into that for nuclear chemistry and the decay process that's associated with it. Okay, so in summary, let's delete this one. So in summary, everything that we talked about today becomes very useful when we're talking about it in terms of biochem, right? So instead of calling it reactants, like we do here for general chemistry or physical chemistry, in bio, it's called the substrate, right? And instead of calling it a catalyst, like what we've seen, inside the body, we call it an enzyme. And instead of calling it reaction rate, when we talk about kinetics inside the body, we call it velocity. Does that make sense? So these are your biochem terms related to what we talked about today in terms of reactants, catalysts, and reaction rate. So we have your substrate, your enzyme, and your velocity. Then this gets into your Michaelis-Menten curves. And then from your Michaelis-Menten curves, you linearize it the same way I just did the linearization for 0, first, and second order for your Lineweaver-Burke plots, right? So this is how we relate it back. Any questions on anything that we've gone over today, from Carnot's engine, thermodynamics, thermochemistry, to kinetics? If not, we'll go and do a passage. We're good? No, there's no more content after the passage. I covered all the contents. Thanks for allowing me the time to go through and do everything and cover everything from relating the difference between thermodynamics, which is the energetics of a reaction, to kinetics, which is the reaction rate or the activation energy associated with the reaction, right? Sure, let's go back to the Boltzmann distribution and the Arrhenius equation. So what a Boltzmann distribution is saying is that you might have a little bit less molecules at a higher temperature, but more of those molecules overall are going to be at a higher temperature, right? Because the average. So you're saying this is the average amount of molecules that are at that temperature for any given temperature, right? This is how molecules are moving. And this is the x-axis is the kinetic energy associated with it. So the further to the left it is, the lower the kinetic energy, or i.e. the slower those molecules are moving. And the further to the right they are on the x-axis, the faster those molecules are moving. So when molecules at a higher temperature, there are more molecules at that higher temperature, or they're moving more quickly. So in terms of reaction rates, it'll be a lot faster, because since they have more kinetic energy, they're moving faster, they're quicker to collide with each other, right? It's not, it's just on the curves. It's just number of molecules versus kinetic energy.
I guess
You gotta
the question is, why is T2 bigger than T1?
There's a greater number of molecules at that temperature are going to be activating at a higher kinetic energy versus the average kinetic energy at temperature 1.
Okay, so this has nothing to do with like the actual like temperature, right?
No, this is actual temperature. Do you remember what the definition of temperature was when we talked about it? When we talked about heat energy, Michaela, back in week 2, work and energy, when I talked with work and energy, forces and work and energy with you? Temperature is average kinetic energy.
Oh, okay.
Yeah.
Okay, so then technically it would be along like the
right?
What was that?
Technically, kinetic energy is temperature. They're directly proportional to each other.
Okay, thank you.
On the micro scale, it's kinetic energy, right? The translation, rotation, and vibration of the gas molecules or the liquid molecules that we have in solution or in a gas form. And the temperature associated with it is just relatively how fast they're moving, right? The collision rate for those molecules. Cool. But yeah, that's where it's coming from.
So is the temperature in T1 not higher than T2?
No.
Like, I think that's what I'm getting confused on.
Look at what my y-axis is. This just means there's number of molecules. That just means there's more molecules at a lower kinetic energy.
Oh, okay, okay. So and the
Y-axis
temperature is
isn't
lower because KE is
Y-axis is
equal.
number of molecules.
Okay.
Okay. All right. There was a question that came in. Can we go over the heat and work values for the Carnot engine in the graph? Okay, sure. So let's go over the Carnot graph itself. So what happened? We put in heat. When this is happening and this is expanding, we got work out or work useful here, right? This is that expansion rate when the piston was going up in the heat engine, when the piston was moving up because that gas rushed in. That's where we got our useful work. Sorry. That's where we got our useful work in our Carnot engine, right? And then when it's cooling down, this is our heat cold that's leaving at this point. Does that answer the question? Someone was asking if what Q and W are and where they are, what they're doing in your Carnot engine. So we're putting in heat here. This heat could be from burning fossil fuels, could be from nuclear, could be from hydro energy, right? Like dams. Could be from burning coal. From A to B, there's no work being done because you're doing it isothermally, right? So there's no change in internal energy of the system. So the heat is equivalent to the work that's being done in the system. So if it's isothermal, remember delta U is proportional to some delta T. So if it's 0 isothermal delta T, that means that Q is equal to negative W at that point. This is from Newton's the first law of thermodynamics, which we covered, right here. Yeah. So delta U is equal to 0 when you have an isothermal process. Does that answer your question? Cool. It's slightly lower. So let's look at the Boltzmann distribution. They're slightly lower. Less molecules are moving at that greater temperature. But if you think about it, all these molecules are moving at even higher temperatures, because if you think of the average, when this one's really tall and narrow, this one's flat and wide. So the distribution of molecules that are greater, that are moving with greater temperature, if you calculate all of these area under the curve, those are for all the different number of molecules. So it's incorrect, Eileen, to say that it's less molecules. Does that make sense? Only if you have a Carnot engine. There was a question, why did I write QC in the graph? If it's a Carnot engine, then it's none. QC is 0 during that compression step. But in real life, we know that you always have some type of exhaust, right? Like think of every structural engineering design thing that you've seen with an engine in it. You always have an exhaust valve, right? That was the nemesis of like the Death Star. It had that exhaust valve. That's why they were able to shoot photon torpedoes down it, or whatever they shot down the thing. But yeah, in real life, everything has an exhaust, and so we know that the energy is going out somewhere because we can't convert it completely. Only in a Carnot engine is that QC is equal to 0. But yes, thanks for pointing that out. There should be no QC at this bottom step right here if it was a Carnot engine. But in real life, we know that there should be some QC since we calculate for that thermal efficiency with that QC over QH. Sorry, I made a mark there. I'm trying to delete it so someone doesn't get confused in your system, right? Correct. Thermal efficiency is 1 for a Carnot engine. It just means how well are you using the energy that you put in, right? So what is efficiency, right? Efficiency is how well that do we take that energy from burning fossil fuels, from nuclear, from charcoal, from whatever we're burning, right, to create heat. How well did we use it? And sadly enough, the highest efficiency things that I've seen out there, 37% efficient. So basically 2/3 of the energy is coming back out. Yeah, 1 means 100% efficient. So if you think about it, most power plants, most any type of engine you see, there's generally like most combustion engines, like in the high 20s, low 30s% efficiency. Yes, this is sad. Where we're burning fuels and then we're giving off all of that heat excess or exhaust, and that's what's leading to all the carbon emissions into the atmosphere. Does that answer the question? Sorry. Cool. Just want to make sure. This is all practical things that comes up quite often. You guys don't think about it, right? When you're driving your vehicles and driving your cars, getting from place to place, because you're like, I got to do things, I got places to go, I got people to see. But all of this bears to weight when you guys are actually looking at and doing all those carbon emissions to the environment. Okay, so let's find the passage real quick, get you guys started, and then we'll go over it. I have a little time after, so we'll spend some time going over it, but not too much. Okay. Any other questions before we do the passage? Because everything on the whiteboard is going to be deleted. Okay, we're good. Share screen. There are 7 questions. I'll give you guys 8.5 minutes because there's a bunch of tables and numbers associated with it. Give you guys 8.5 minutes. You guys may begin. I will not be checking questions during this time. I'm going to give you guys a time so that I won't go back and forth between screens so you can see and read and do everything. That is time. Hopefully you guys got a chance to do it, go through it. All right, let's take some time. Make sure we can go through and do this type of passage. So number 21. So we're looking at the products as a function of time, right? So we have a second order reaction that's occurring that we know. So we really should be mirroring this graph and doing like the reverse, right? Getting to here. Does that make sense? So which of these data point ones is going to give us that closest? So it looks like it jumps up. It's pretty steep in the beginning, so it has to have a biggest drastic change. That eliminates C, that eliminates B, right? The drastic change for B happens from 0.3 to 0.9, not at the beginning. This one is slightly at the beginning. And then we look at it relative into the concentrations of your reactants that you have. You should have a little bit less because it's squared, right? So this one's almost 1-for-1 for D. It looks like it would have been first order, so A is your best answer choice. Any questions on how we got A? Cool. (22) What would be observed for the concentration of time if the initial reactant concentration were doubled? They're looking at zero order and first order reactions, right? So for both zero order and first order reactions, the concentration at any given time would be doubled. It's definitely not zero order because when we look at it, first of all, zero order depends on none of the reactants. But if we graph zero order graph from the one on page 236, 237, this was your zero order graph, right? If we double the concentration from here to here at this given time versus that, right? Is this doubled? It looks like it's way more. This is for the 0th order graph as it changes reaction rates from page to whatever. This is like way more, even though we doubled the initial concentrations. This is initial concentration. This is 2 times that. Look, double would have been at a specific point. The only time where it's doubled is if this is equivalent to this. Does that make sense? So it only happens for first order. So we graph the first order. This is your first order graph. We double the concentration of that. It's like somewhere up here. So at any given point that I graph it, these two things are roughly the same. Any point that I graph it, these two differences are roughly the same. So the concentrations always remain double at any given point. Okay. Does that make sense, Michaela? Yeah, it's just like understanding what those graphs look like and how much curvature there is to the graph. Yeah. Back to question 23. What is the half-life for the sample first order reaction? So you know that it goes half when it's half of the initial concentration. Initial concentration was 1 molarity. So 0.5 molarity is somewhere between 1 and 2, right? And it's closer to 2 than it is to 1. So it almost looks like it's halfway through between the two. So the best answer choice there would have been C. Right? Closer to 2, but somewhere halfway between 1 and 2. Because half-life would have occurred right here, right? At 0.5 molarity. Oh, 22 was first order. Yeah, only first order is doubled. Sorry. 23 is C. 24. Which of the following statements are valid respect to chemical kinetics? Half-life is constant for first order. We know that for a fact. Addition of a catalyst can reduce the half-life for a reaction, right? It changes the rates, right? So that's true. Second order reactions speed up over time. Ooh, that is not true, right? It takes longer for those second order reactions to happen over time, right? Think of the half-life of those second order reactions. They double in time for every half-life. So that is a false statement. Half-life is constant for first order kinetics. That's true. Look at page 236, 237. Addition of a catalyst can reduce the half-life for a reaction. Catalysts change reaction rates. They increase reaction rates, right? By stressing a lower transition state. Which of the following relation accurately depicts the half-life for first order reaction? ln of 2 over k. I gave that to you. 25 is A. 26, and you can also calculate it, right? It's C is equal to C naught e to the negative kt. So C becomes 1/2 of C naught is equal to C e to the negative kt. Get rid of the C naught. We're going to get ln of 2 is equal to 2 to the negative 1 is equal to negative kt. Bring the negatives over, and you'll see that kt is equal to ln of 2. We get rid of the negatives because that negative 1 gets brought out in front, and that negative cancels out, right, with the negative. So then t becomes ln of 2 all over k. That's all we did for 25. Cool. Which of the following pairs of time describes the half-life for a standard second order reaction? If first half-life, the time has to be double for the second half-life, right? So 30, 60, A looks good. 30, 120, that's no good. 120, 30, no good. 60, 30, no good. So A is the correct answer to 26. And then we know that for zero order, it's linear. So A is the best answer. Concentration is a function of time. Cool. Any questions on any of these? Sure, I can go over 21 again. Sorry, and then I'll go over 26. Not D, because the half-life, I'll do this and then I'll go over 21. Sorry about that. ALAP. It's T, then 2T, then 4T, so on and so forth for each of the half-lives. First, second, third. So this is the opposite. It starts at 60, then it becomes half of that. That's a zero order. Not a second order. For number 26. Okay. So when you see that trend, you know that this is zero order and the other one was second order. Okay, so 21. Let's go over it again. So we know that we're looking for the products, which is going to happen just as quickly, right? It's almost like a mirror image of your decay graph, right? Your growth curve. So we know that there's going to need to be a big change at the beginning. That's how I canceled out B and C, right? It starts off really at 0, then it goes, it's very sharp and steep at the beginning for this curve. Okay, just like this was sharp and steep to decline. Right, so now I'm at A and D. We're good there, Ayla? Good. So now if we look at D, these numbers versus this number, if you think about it, it's greater than 1. How's that possible? How are we making more mass than entirely possible, right? For each individual point. So that's why I chose this A over D. They're both decreasing, but this one decreases, like it gets flatter quicker. So this 0.19, 0.76, 0.3. This is so like 0.22, 0.15, 0.1. So the with second order kinetics, it gets flat really quick. And so this one shows a flatter stopping. This one is still fairly steep for D between A and D. Does that make sense? I'm just looking at the difference between each of the successive steps between them. And so since second order takes longer to go down, that curve flattens out way, way, way more, right? So that means there's very little change from each of those time steps. Cool. All right. If there are no other questions, I will see you guys next. Shoot, I'll see you guys in like 2 weeks or something. I won't see you guys next week. Shucks. Okay, I will still have office hours on Monday, 4 to 5. If you guys have questions, I'll be there 4 to 5 after the lecture. If you guys have any other questions, feel free to email me and let me know. I'll have office hours tomorrow from 12 to 2. I've been asked to change it because just not a lot of people were coming from 11 to noon. Okay, so let everyone else know. I'm going to send out an email to remind everyone about office hours for tomorrow, and I will see you guys in 2 weeks. Okay, but I'll still have office hours on Thursdays and Mondays still. Okay, talk to you guys then. Have a good night. Jonathan, Mo, Sarai, do you guys have any questions? Well, I'm here for questions. If you guys have any, I'll be here until 4:45. What's the thing?
Call has been forwarded to an
it.